Hi, everyone. It's a pleasure that you could join us today. We're going to be talking about two papers that we've recently written, and this is an academic presentation of those two papers. Waymo is kind of usual or unusual, with that we write papers. We've written over 20 papers, and we do that so that we can be transparent and we can speak to the details and talk about the many different aspects of safety and how we measure safety. But before we go into the papers themselves, I want to contextualize a little bit. So we've argued or advocated for a safety case approach. A safety case approach is a set of arguments that back up a goal, and the overarching goal is absence of unreasonable risk. And absence of unreasonable risk can be determined with many different methodologies, or it is determined with many different methodologies. We separate operational hazards, the yellow on the top, from risk assessment of behavioral hazards in the middle, and we have architectural hazards. So this is a complex topic, and today we'll be talking about one topic. We'll be talking about the aggregate crash statistics. And it is important, though, to realize that our approach relies on multiple methods to measure each of these things. And we do look at performance, and we measure safety both at the aggregate level as well as at the event level. And that the safety case is in operation. We do a product readiness determination, and those are the green dots at the top. And each of these readiness determinations are done for software releases. And so what we've been doing in the past is we've been scaling, and where we are today is we're accumulating more data. So off on the right, you see that we're now able to talk to the aggregate performance and view safety as continuous confidence growth in our crash outcomes that we've accumulated when we drive rider only, which is without a human behind the steering wheel. So it's a topic that's kind of easy. You compare the performance on crashes of the human with the autonomous vehicle, and it's really just for simple numbers. But behind those numbers, there's a lot of challenges. And those challenges are what we want to talk about today. And it's a science. This is the safety impact science. Epidemiologists and statisticians have been working on this topic for many years. So today we'll talk about two papers. One is the benchmark paper. A benchmark is to create a comparable set of crashes that are driven within an environment that is comparable. So it's apples to apples comparisons, and how we get to those apples to apples comparisons. And once that's established, once we know those numbers, then we can use that in the performance study. So we compare the behavior of our Waymo Driver to these benchmarks over 7.14 million miles of fully autonomous operations in Phoenix, San Francisco, and Los Angeles. And that is when there's no one behind the steering wheel. So that's actually what's unique about these studies, is that we are looking at crash rates where there's no one behind the steering wheel. That's the only data set we're looking at this time. So it's called rider only. And we're looking at all crash rates. So it's both when we are contributing to the crash as well as when we're not contributing to the crash. We're also looking at all crashes, and these crashes were reported in the standing general order required by NHTSA. So they are publicly available, and these crashes include any amount of property damage and any injury, regardless of responsibility, if Waymo was responsible for the crash or not. So indeed, we're using publicly available data, and that means that you can replicate these results. In the appendices, we identify which crashes we're using, and you can follow along on how the benchmarks were determined. So part of the benchmark, the challenge is to correct for common biases. And with biases, it's a statistical bias that we're talking about. And these are things that you need to correct for or adjust for. But there's also some other misconceptions when calculating crash rates that we'll address in more detail. So the first study, I'll hand it over to John Scanlon.
Hi, everyone. My name's John Scanlon, and thank you for that introduction, Trent. So I've been at Waymo for a few years, and I've been very much looking forward to the opportunity to talk about some of our benchmarks that we have here at Waymo. We have lots of them, using lots of different data, and this is one small piece of that large benchmark work that we do. So benchmarking ADS performance is not new to the scientific discipline. And benchmarks in safety impact analysis is not new in automotive safety. It's been around for many decades. But for the last 8 years, in terms of evaluating ADS performance, there have been a number of studies that have aimed to generate benchmarks that are representative of the fleet that the ADS population is replacing. So why do another study? And that's because, in this discipline, it's important to continue to build upon the existing literature and continue to advance it. And there's also other fundamental reasons why. So one major reason is that every year, a new crash and mileage data is released. And it's important to update your benchmarks with this latest data because crash rates vary by year to year. The second reason is because the ADS driving region is changing. Waymo is deployed in San Francisco, Los Angeles, and Phoenix, and having benchmarks for those new areas is important for then the evaluation within those areas. The third thing is that a lot of these prior studies focused on one or two narrow severity outcome levels. So as a part of this study, we wanted to look at a range of different outcome levels, understanding the relative rates of each of them, and then we actually perform a power analysis within the study itself in order to kind of investigate how many miles would it take at a given efficacy to establish statistical significance. And then the final reason for doing this, and Trent hinted on it, is that these studies, as it naturally is in science, evolve from one another, from the past study, and they're constantly correcting and improving on the prior work. As a part of this work, we do a literature review of the existing studies out there, and we continue to advance it, including identifying these common statistical biases and just continuing to elevate it. Even this idea of correcting for these biases is not something new. There's actually been a book even written on it. Yeah, just calling that out. And then, okay, so teasing this idea of common statistical biases and misconceptions, what are those? So here we've laid out 5 general categories of what we've observed when looking at the existing literature. The first thing is that when you're working with benchmarking ADS performance with human crash data, on the ADS side, you're generally working with NHTSA SGO, which is NHTSA SGO data. And to be included in that data set, there has to be any level of property damage or any injury. When working on the human data side, it's also any injury, but on the property damage side, there's actually a property damage threshold that's been set. So there's this gap between below the threshold that's missing from the data. And there are measures that can be taken to help correct for that bias, and we'll talk about some of that. The second thing is that there's naturally some underreporting in human crash data. On the human crash side, there can be different factors that would dictate that if I was involved in a crash, whether it was actually reported to police, whether the police actually made a report, even if it was eligible for a report, and then even if it was reported, would it actually have showed up in, let's say, a state crash database? So we'll touch on a few of those different sources in the study and show how we're correcting for it, when we can. The third thing is there is when you're looking at all of human crash data, it's not necessarily all representative of the ADS driving. So there's certain things you should do to match for that ODD of the ADS driver. The fourth thing, and I'll get into this because it's a bit of a nuanced topic, is that we've seen historically there have been multiple times where vehicle level crash rates have been confused with crash level crash rates. And I won't bore you with the details right this second, but I'll give an example in a few slides that kind of walking you through this. And then the last thing is, because crash and mileage data is collected independently with its own data features, it's important that whatever you do on your crash data, whatever sort of procedures you do, are done equivalently on your mileage data. So. Okay, so one really excellent part about the study, one reason why I was so excited to do it, is because we only relied on data that's publicly accessible. And in the US, we have a few different data sources for being able to capture crash rates. First, on the national level, we have data collected by NHTSA. In this study, we relied on CRSS and FARS for crash data. And then for mileage data, we actually relied on FHWA, highway traffic safety statistics for understanding what the vehicle miles traveled were on national roadways. And then on a county level, we use state databases from both Arizona and California for making estimates of the crash and mileage data. These are all, again, publicly accessible. Anyone can go and download these. In Arizona, it comes directly from the Arizona Department of Transportation. And then in California, it comes from a combination of the California Highway Patrol and the SWTRS database for crash data. And then for mileage, it comes from Caltrans. Okay, as I noted before, we wanted to investigate multiple different outcome levels when doing the study. When you're looking at human police reported data, the threshold for what's included is about at the police reported level, where you have some police report. Within that police report, there may have been any injury reported, then it could have been a towaway, or there could have been a fatality that was involved. If you want to extrapolate up to that A bullet point there, that any property damage or injury threshold, you have to do an adjustment on the data. And it turns out that there's multiple methods in the literature for how you could do this adjustment. And we use these previously established methods. The first method comes from a NHTSA study that used telephone surveys and insurance data to help estimate how many crashes were the amount of underreporting from police reported data. And they came up with an estimate of 60% of property damage only crashes and 32% of non-fatal injury crashes were not reported in police reported data. In a separate study by Blanco et al., which was a VTTI study that used SHARP2 data, this is naturalistic driving data, they also wanted to get at this question and see the amount of underreporting that occurred from these data. And in their estimate, they estimated that 84% of property damage only crashes were not reported. So what we did in this study is we used both of those adjustments on the police reported data to help get at those estimates. And then also for the any injury reported data, we used the NHTSA study to help make that estimate as well. And rather than rely on any single one of these variable or these data, we are using all of these estimates in our analysis. Okay, as I mentioned before, there has been some confusion around vehicle level and crash level crash rates in the literature. For some groups of researchers, they do it right every time, and in others, there's occasionally a mistake. So I have an example to help walk through how to do this properly. So with an automated driving system, it drives a certain amount of miles, and during those amount of miles, some amount of crashes are experienced by that vehicle. So every one of those crashes counts, and then the mileage is counting. And then you take the crashes over the mileage, and you get a vehicle level crash rate. That's the number of times the vehicle crashed per vehicle miles traveled. When working with crash data, and for all the nerds like me that have used crash data out there, you know that there's a crash table where every row in the table refers to a crash, and then there's a vehicle table where every row on the table is a vehicle that was involved in those crashes. When doing a vehicle level crash rate from police reported data, you have to use the vehicle level, you have to use the vehicle table, where every one of those is a crashed vehicle, and then you divide that by the total number of vehicle miles traveled. So that is what a vehicle level crash rate is. When looking at national data in the US, if you fail to do a vehicle level correction, you're missing a 1.8 multiplier, because on average, there are 1.8 vehicles in every crash in the police reported crash in the US. So you have to, again, do this vehicle level correction. So I hope that gets the point across. If it didn't, I highly recommend that you read the paper where we go into much more detail about this. And it's very important to capture this. And I also have a reference for a study that has done this properly in the past. And yeah. Okay, so a big part of this study was capturing the automated driving system driving environment in the human crash data. So in the human crash data, you have all sorts of vehicles. You have golf carts, you have motorcycles, you have combination heavy trucks. And when you're doing a crash rate and you don't control for them, as you can see on the graph on the right, if you don't control for those, your rate is slightly lower. So what that means is that passenger vehicles tend to have a slightly higher crash rate than the rest of that crash population when it's all combined together. So you have to control for only passenger vehicles in generating a crash rate. In addition to that, and this is also a well-known fact in the in crash rate analysis of human crashes, crash rates on highways tend to be lower than on surface streets. So you also have to control for the road type. And the reason that's important is because the Waymo Driver is currently deployed on surface streets and is a part of their commercial deployment. So when you correct for that bias, that if you don't correct for it is a bias, you get this other large jump there. So if you see on the graph, that's that final data point on the right. So it's important to control for both of these. And I just wanted to call that out here, that we present all of these intermediate values just to show what would happen if you didn't control for these factors. Okay. All right. So I'll now jump into the results here. First, introducing that graph on the left. On the y-axis, you have incidents per million miles. And these are, again, a crashed vehicle rate. And then on the x-axis, you have various levels of severity. And I kind of have them ordered in terms of how frequently they occur. Where every data point here is a crash rate from our analysis that you can actually go and look up in a table to see exactly what that number is. Okay, so the first thing I wanted to point out from this graph is just the vast difference in rate between that highest level, fatals, and then the lowest level, any property damage or injury. There's a 1000x difference in the rate. And what that means from a statistical assertion standpoint is you're able to make statistical claims earlier with rates that are much higher because you would expect them to happen more frequently. So lack of them under a more limited amount of miles is when you're able to make statistical assessments. So it's important to kind of consider the relative rate here. The second thing is that there's, as I mentioned before, we're having to do underreporting adjustments. As you move rightward, you don't have to make these adjustments anymore, and the imprecision due to these adjustments goes down. So in general, the data becomes more powerful as you move more rightward in terms of precision. And the third and final thing, and I haven't touched on this yet, but in California, SWITR's data, again, this is a state database, there is an interesting inclusion requirement that's listed in the manual and it's listed in California code, that there has to be all crashes where an injury happened have to be reported into this database. If there wasn't an injury reported, the police report does not have to make it into the database. So even if a local jurisdiction in like San Francisco or Los Angeles had a crash with property damage only where a police report was written, it wouldn't have necessarily been sent to the state database. And you can see it here in the data where around number 3 is that you'd expect to the left there for the rates to be much higher than they are because, because of this potential missingness and property damage only. So as I move to the last slide and talking about limitations, again, harping on this point of potential missed data in California, you see there on the right percentage of property damage only crashes that are in police reported data. When looking at the national data, about 70% of police reported data are property damage only. That number is also what it looks like in Phoenix. But when you look at San Francisco and Los Angeles, there's a much higher proportion of crashes that are injury crashes and a much lower proportion than you'd expect that are property damage only crashes, which we suspect is likely because of undercounting in the SWTR's database of the actual police reported crashes. Again, by design, but just noting that as a consideration when looking at the study. And that would lead to an underestimation of the actual human crash rate. The second thing is that the purpose of this study was to generate a crash rate that's reflective of the current driving population, because that's what allows you to estimate what the current safety benefits of the system is. There are other benchmarks out there. Like you could look at a higher performing driver, and that's, but it's not something that would enable this sort of safety impact analysis in the current fleet. So that's what we focus on for this current study. The third thing is that we're leveraging the most recent data year available across all the data sources, which is 2021. Crash rates do vary from year to year, as I mentioned before. And as 2022 and 2023 become available across all the data sources, we'll again repeat the process. The fourth thing here is that we're using some custom methodology for kind of doing the classification of passenger vehicle and road type, using these databases that are all unique from one another. There aren't any standards on this methodology. In a way to be transparent, we have a very lengthy paper and appendix showing this methodology, so anyone can replicate our results. But we do want to note the general, it would be awesome if there was a standard around this. And then the fifth and final thing is that the data sources are only so granular and it limits our ability to control for all the different driving factors that could be potentially influential here, like time of day, driving density, but future work will cover this. So, yep, thank you for your time, and I'll pass it over to Chris.
All right, thank you very much. My name is Chris Kusano, and I'm a safety researcher here at Waymo. And I'd like to talk a little bit about the second paper, which was a comparison of the Waymo RO and human benchmark crash rates. The data source for this study was DITSA's standing general order. And this is a order from the government that has required all ADS operators like Waymo to report all collisions that are involving or alleged to have involved the ADS vehicle that result in any amount of property damage, injury, or fatalities. This data is publicly available on NHTSA's website, which I'm showing a screenshot of here. The only thing that's not required to be reported is the miles driven in all locations. This is required in some places like California, but outside of California, generally, ADS operators are not required to report mileage. And so for this reason, we only analyze Waymo crashes in this study because, of course, we know how many miles we drove in each location. So this slide just is going to step through some of the data selection criteria. So we used the SGO data, and we found collisions that were reported by Waymo. And the way we knew it was an RO collision is if the driver operator type equals none, meaning there's no driver. This is because we also have to report collisions involving Waymo vehicles with the test driver or autonomous specialist behind the steering wheel. And so we only, again, are analyzing RO collisions in this study. We did have two exclusions from these comparisons that we did to the benchmarks. The first one was we excluded not in transport vehicles. What this means is that if the ADS vehicle is in park gear and in a valid parking spot, meaning close to the curb, on-street parking, or in a marked parking spot, we didn't compare it. And this is because in crash databases, which John just talked about, these parked vehicles are not included as vehicles. They're counted as objects. And furthermore, it doesn't really make sense to calculate a rate per collision rate per miles traveled for parked vehicles because they're not accumulating miles. We did include not in transport vehicles for the naturalistic benchmark comparisons. And this is because it wasn't really clear from those studies whether they excluded not in transport. And so just to be conservative, we included them in this comparison. The second exclusion was when the ADS vehicle was not impacted. And as I mentioned before, we were required to report to the SGO if there was an alleged contribution to a collision. So this means that the ADS may have done something that contributed to a collision, but they were not impacted. And again, these are not included in any sort of crash database. It requires that a vehicle is damaged to show up in the vehicle count there. And so on the right side of the slide, we use the same three outcome groups that John just talked about. The first one was any property damage or injury, and this included all SGO reported collisions. The second one was police reported, and we used the SGO report field law enforcement investigating, and we included whenever it said yes or unknown. I won't go into the details here. There's an appendix in the paper that describes what we did for police reports. But our approach here was to be conservative as possible. We checked our records that we had from our operational records, our insurance records, and what we found was that to be conservative, we just included anytime it was yes or unknown. The last outcome group was any injury reported, and again, we used the SGO field highest injury severity alleged, and anytime it said it did not say no injuries, then we counted this as an any injury reported collision. And for this study, there were only minor injuries included in this data set. So this table shows the same outcome groups in Waymo data and adds which human benchmarks we compared to for each category. So the first comparison we did was to the any property damage or injury with the Blanco adjustment that John just talked about. And we also compared to a few other studies in the literature. The first one was a study by Flanagan et al. That recently estimated the collision rate for a ride-hailing fleet in San Francisco. So we compared this to all of our San Francisco Waymo collisions. And then the third study here is the Blanco et al. This is the SHARP2 NDS collision rate. And because this study was conducted in several cities in the country, we just compared all of the Waymo collisions in all locations as kind of a national estimate. For the police reported and the any injury reported, as John was mentioning, we think that the updated benchmarks in the locations where we're operating in are the most up-to-date and most valid comparisons. And so we used the Scanlon et al. Police reported and any injury Blanco adjusted. So just a quick note on the confidence intervals we used. We had two types of confidence intervals that you'll see. We estimated confidence intervals for incidents per mile, or IPM. And for this, we use the Poisson exact method. This is a little more conservative for small event counts like we have in the ADS data, as opposed to a normal approximation of the Poisson, which is commonly used. The second confidence interval we computed was for the ratio of the ADS to human crash vehicle rate. And the interpretation of this is if this ratio is greater than 1, then the ADS has more collisions than the benchmark. And if it's less than 1, then the ADS has fewer collisions than the benchmark. And if this confidence interval does not include 1 in the interval, then you can say that the ADS has a statistically significant difference from the benchmark. And just a note on the next slides, I'm going to be not showing this ratio directly. I'm going to show this as a % reduction. And this is just a scalar transformation to this ratio. We present both in the paper. You can refer to that. Okay, so here are the results. This slide shows the Waymo RO reduction in police reported and any injury reported crash rate. Along the horizontal axis here is shown the different locations that we analyzed. So Phoenix, San Francisco, all locations together where the benchmark is blended proportional to the number of miles we drove in each location, and then all locations compared to a national benchmark. And then the blue bars show the reduction the ADS had on the rate of police reported collisions. And you can see that the reduction was between 51 and 57% and was statistically significant in all of the locations shown here. The second comparison we did was the any injury reported collisions, the dark green bars, and this is using the underreporting adjustment. And that reduction varied between 76% and 90% and was also statistically significant in these locations. The third comparison we're showing up here is to the any injury reported observed, so unadjusted benchmark. And the reason why we're showing this comparison is as a sensitivity study for this underreporting adjustment. We know there is underreporting, and so we think the most valid comparison is this adjustment. But just for the sake of comparison, if you didn't account for that, you get kind of the same answer. The magnitude is slightly decreased, of course, because the benchmark rate becomes lower. And the other difference you'll see is that some of the locations, Phoenix and the national comparison, are no longer statistically significant due to a low event count. And so what we conclude from this sensitivity analysis is that the assumed underreporting correction has only a small effect on the results. So now I want to switch gears into the any property damage outcome category. And as John was alluding to, there's a lot of variability in these estimates. So this chart that I'm showing on the left side is the benchmark collision rates with confidence intervals. And again, shown on the horizontal axis as, vertical axis as an IPMM. And along the horizontal axis is the location. And so you can see the blue and the black dots are the Blanco adjusted and Blinko adjusted police reported derived rates. And you can see first that there's a lot of discrepancy between those. So there's a big range in underreporting assumed between these two data sources we have. The second thing I'll highlight is that this naturalistic study derived ride hailing benchmark from Flanagan et al. Is much larger in San Francisco than the police reported rates. And that leads to the third observation, which John also just touched on, is that we know there's systematic underreporting in California in the Switters database. And we used the same underreporting estimates in all locations. So we know this doesn't account for that systematic underreporting. And this sort of like raises alarm bells here that like it's a well-known correlation between population density and collision rate, independent of miles. And it just doesn't make sense that there's fewer collisions expected in San Francisco compared to Phoenix, just because the population density in San Francisco is so much larger. And so all of this variability together makes drawing conclusions about this any property damage or injury category difficult. And it's pointing toward that we need to do more research or find better data sources that can better correct for some of these different types of biases that might be affecting these benchmarks. Nevertheless, we did do the comparisons to the Waymo RO, any property damage or injury, crash rate, and these benchmarks. And the graph on the left shows similar than what I showed before. It shows all of the SGO reported collisions were compared to those benchmarks. And you can see that because of this variability in the benchmarks, you get a different answer depending on which benchmark you use. And as additional sensitivity analysis, we did a second comparison that's shown on the right. This shows all SGO reported collisions for the Waymo, but we excluded any collision where the delta V, or the change in velocity during the collision, was less than 1 mile per hour. And so these are very minor collisions that are unlikely to be picked up by the vehicle's event data recorder. If the vehicle is stationary, then it probably doesn't even move the vehicle tires. It probably just rocks the vehicle on its suspension. And so this 1 mile per hour delta V condition applies to 48% of the Waymo SGO reported collisions. And so we're not saying this is necessarily a valid comparison to make, or that this is the one you should use, but it just shows that a very small adjustment in the minimum reporting threshold does make a big difference on interpretation of results. And this is another area, in addition to getting a better handle on the benchmarks, having a more defined minimum reporting threshold between the benchmark data and the ADS data will probably improve the validity of these comparisons. So this study also has some limitations, and I listed 3 here. First, this is using aggregate collision rates over a long period of time. Of course, as John was mentioning, the service has changed. We're driving in different parts of the city now. We don't think this is a long-term problem. As we start to drive more, we'll have more miles to restrict this to a shorter period of time. The second limitation is the benchmarks did adjust for these common factors that are kind of pointed out in the literature: the location, the road type, the vehicle type, but other factors that may affect the crash rate, like how much driving you do in a certain location in the city or the time of day, those aren't available in the benchmark data, and particularly in the VMT sources that give us human miles driven. And then the last one that I'll highlight is that this study used outcome-based measures, so the number of observed police reports, injuries. There may be utility in using risk-based measures, using injury risk functions, and this is commonly done in the active safety and ADAS safety impact literature. This just allows you to control for more differences between your benchmark population and the ADS population, like seatbelt use, the age of the vehicles, and so on. And just to conclude both of the studies, we started out by saying that retrospective crash rates are one, but not the only aspect of determining ADS safety, and I just want to reiterate that again. The benchmark study that John talked about provides an updated benchmark for comparisons between ADS and human data that control for important factors cited in the literature, as well as from recent data from the cities where the ADS currently operates. And then the RO performance study found that we had a significant decrease in police reported and any injury crashed vehicle rate. And on the right of this slide, I find it useful sometimes to put these in real terms. It's sometimes a little easier to understand, or kind of gives you different insights. And so what the numbers on the right are showing, that if you had a human driver that had the same collision rate as the benchmark, and they drove the same 7.1 million mile distances, then you replace that driving with the Waymo Driver, you would have 8 fewer injury crashes and 13 fewer police reported crashes in Phoenix, and 9 fewer injury crashes and 7 fewer police reported crashes in San Francisco. And this sort of highlights the differences in the benchmarks and the different risks in different cities. As you'll recall, San Francisco has a much higher injury rate than Phoenix. And so even though we drove less in San Francisco, it actually has a higher benefit in preventing injury crashes compared to Phoenix. And with that, I will thank you very much for your attention today, and I hope you enjoyed it.